discuss the continuity of the composite function hx equal to f parenthesis gx. In order to solve these questions, we need to understand what this means. So basically, we are plugging gx into fx here, right? Okay, which means you are plugging this function into here basically. So in this case, I can rewrite this f gx equal to, as you know, gx equal to this one. So this can be replaced in the parentheses. So it's going to be f x minus 1. It means you input x minus 1, this x minus 1, into x right here. Okay, so it becomes 1 over square root x minus 1. So end up we got hx equal to f gx equals 1 over square root x minus 1. Now let's think about continuity for this function. As you know, this is one of the rational function. The rational function case, the denominator cannot be the 0. At the same time, the property, domain of the radical equation, especially square root, the inside of value must be bigger than or equal to 0. So I'm gonna set up radical function property first. So x minus 1 must be greater than or equal to 0. So you combine 1 here. Then x must be greater than or equal to 1. Now, since it is on the denominator here, right? So we need to avoid it will be 0 case. So in this case, if x equal to 1, then it's going to be undefined. So we disregard equal sign here. So x must be bigger than 1. Therefore, this answer must be interval 1 to infinity. This function is continuous. Next section is infinite limit. Then what does infinite limit means? And then what are all the property of infinite limit? Please describe it as looking at page 83. This is section 1.5. And then read all this section, especially if you're looking at page 87. You will see property of the infinite limit. So I'm not going to solve 14 and 15 for you. Just leave it those questions so that we can talk about this topic next week. Good? Determine all vertical asymptotes of the graph of fx equal to x squared plus 2x minus 8 over x squared minus 4. Please make sure you watch this video before reviewing page 83 to 87. Okay, then let's start solving these questions. Vertical asymptote located on the denominator basically, because the reason the vertical asymptote occurred, so the case function has undefined value. As you know, undefined value we can find from the denominator equal to 0, right? However, this case, you see another expression on numerator, also on denominator. So like last time, we talked about this continuous value, especially removable and non-removable discontinuous value, you need to factor out and then check out whether anything you can remove and then which one you cannot remove. So if you factor this out, then this is going to be x plus 4 x minus 2 over x minus 2 and then x plus 2. Therefore, we can remove x minus 2 this case. So it means at x minus 2, we have removable discontinuous value exists. And now, x plus 2, this is non-removable discontinuous value. So the vertical asymptote located right here. Okay? Therefore, just to make x plus 2 equal to 0 and minus 2, then x equal to negative 2 here. There will be this function's vertical asymptote. Okay, the next question here. Find the infinite limit. So, infinite limit also located on vertical asymptote. As you know, so this function is same as from here. So, where x equal minus 2, infinite limit will be located anyway, right? So, since we can simplify this function x plus 4 over x plus 2, right? I will use x plus 4 over x plus 2 and then analyze infinite limit. Now, if you test out a very close value to negative 2, such as just using several values here, maybe negative 1.9999, and then another one, so this is on the right side, and then on the negative side, maybe negative 2.00001, then you will have 2.0001 and then negative 1.9999. So based on this, if you maybe plug even smaller, like negative 1.999999, then it's going to be 2.000001 and negative 1.9999999, then you will get even bigger, 2.000001. So which means so limit x move to negative 2 from the positive side fx is going toward positive infinity, and limit x move to negative 2 from negative side fx must be negative infinity. So infinite limit exists at x equal negative 2.